Hi everyone and welcome back to the AI Concepts with Coding from Scratch series. In this video, you will learn about the decision tree algorithm in machine learning as well as how can a coding a decision tree from scratch using Python. We are not going to using here any external module like Scikit-Learn, TensorFlow or PyTorch. If you want to learn Python, data science, machine learning and GenAI, subscribe my YouTube channel. What is a decision tree? A decision tree is a supervised learning technique that can be used for both solving the classification and the regression problem, but it mostly prepared for solving the classification problem. And this decision tree is nothing but one tree structure classifier. Let's try to clarify it more, the decision tree, by taking one examples. So we have one table having some feature column just like the gender and occupations and also some suggestions. In the suggestion block, you can see here we have the three suggestions. One is the Free Fire, and you have the GitHub and the WhatsApp. And in the gender section, you have the two gender, female and the male. As well as in the occupation, we have the two occupations. One is a student and one is a programmer. If you see it clearly, or if you try to deep inside this table, you can see that if the occupation is nothing with the student, he obviously open one Free Fire account, or he may play the Free Fire. In the section of the student, you can see student, he maybe play the Free Fire. And if I go to the student, it's not a problem on here if the started from it coming from the female or the male. So you can see here it will playing the Free Fire that you can see. But if he's a programmer, if he's a programmer or she is a programmer, it have the two choices. One is the GitHub, another one is the WhatsApp. He may either open the GitHub account or push the code from that, or otherwise he'll open the WhatsApp and try to chatting in the form of programming articles in the programming forum in Mappy. Okay, so you can see here for the female, if it is a student, it will play the Free Fire. That's mean we have the constant value called the student. Now you can simply go into implementing this whole table in the form of if and the else cases. So if the occupation is nothing but one a student, so we can directly say that he may play the Free Fire or open the Free Fire account. Now, otherwise, if he is a programmer or she is a programmer, he may be open in the GitHub, or he may or she may open in the WhatsApp. We don't know that who is he's a male or the female. But in this section, you can see that if the vendor is nothing but a male, he obviously open in the GitHub. See, because in the section you can see, in the table you can see that actually pronouncing these one as the sections. Because this is one section one, this is section two. I just divided the screen in this person. That's why. So you can see that if the Xander is nothing but one male, he is not going to go into WhatsApp. So he will open the GitHub and try to push the code on here. So you can see here gender is nothing but an male. It will directly go to the printing in the GitHub. Otherwise, it will printing here the WhatsApp. Just jokes apart, okay? Because male and female can be also a programmer. They can also open the GitHub account. Now in the sections, in this discussion, you can see that we simply going to deriving this table into one if and else statement. That's mean what is decision here? See, we also taking the decisions, but we are not creating here tree yet. See, we are not creating the tree yet, but we're taking the decision. But how? We're taking the decision based on the if and else cases. That's mean decision tree is nothing but one combination of nested if else. That's mean it have the multiple number of if and else statement. This is called decision. But how are the tree? Let's go on the next slide. You can see the tree right now. So you can see that that's our code, or you can say pseudo code. If the occupations is nothing but the student, it will directly go to the Free Fire. That we're creating here on node. See, when you actually try to do the coding part, you have the knowledge of the tree structure, tree data structure. So in the tree data structure, we having one root node, and you have the left child and also have the right child. Okay, and also have the leaf node. So what you can say, you can see here is occupation is student. It will directly go to the ES Free Fire. If it is yes, it will directly go to the Free Fire. And if it is no, it will checking for the gender. If the gender is male, if the gender is male, if it is yes, it will go to the GitHub. Otherwise, it will go to the WhatsApp. So this is how internally it will creating the tree inside the decisions. Okay, this is why it's called the decision tree. Also one tree structure based classifier. Let's go on the next slide. So I'm going to taking here on examples. If I go back, You can see here we're taking all the examples in the form of categorical variable, but if you have the numerical variable, how can you handle them? So let's go on here. So you can see here we're taking one examples from the iris dataset. So you have the pattern length, you have the sepal length, and you have the type. So how many types we have? We have the three type. So Setusa, versicolor, and the Virginica that you can see on here. So you can see here those value as nothing but in numerical. But you can also observe one more thing here. In the pattern length, if the pattern length for the Setusa, all the values less than 2, all the values less than 2. So you can also creating here one if statement block. Let's say if the pattern length is less than 2.0, so you can say that it is a Setusa that you can see on here. So you're directly creating here one node. So if the pattern length is less than 2.0, you can directly say that it is nothing but one Setusa. It's nothing but one Setusa. If it is no, then you're checking for the sepal length. So for the sepal length, we have the two choice. One is the versicolor and another is called the Virginica. So if the sepal length is nothing but less than 1.5, because if the sepal length is less than 1.5 for the versicolor, so you can directly say that this is a versicolor. Otherwise, this is a Virginica. Simple thing, you can do it for the numerical analysis as well. I mean, for the numerical data. Okay, so you see that we can handling for the categorical data, we can handle it for the numerical data as well. Now let's go on the next slide. So I'm simply going to plotting this out in one 2D plot by checking the geometrical intuitions. So what I can do, I'm simply going to actually plotting this out in a scatter plot of all our data point. I mean this data point. I'm not actually taking the real data point here. I'm just going to give you some random data point on here. So this portion is less than 2.0. I mean 2.0 is nothing but going for the Setusa. So in portion, I simply going to taking this one 2.0. If the 2.0 is those portion is nothing but for the Setusa flower. Is for the Setusa flower. You can see on here. That's mean this portion of the data point is actually derived from this Setusa flower. If any of the task data is coming in here, we can directly say this data point is about to Setusa flower. Now what about the another one? What about the another one? So rest of them is nothing but in the form of Virginica or the versicolor. Rest of them. So if it is no, then it will checking for the sepal length. If the sepal length is less than 1.5, we can, if it is yes, we can go to the versicolor. So we have the 1.5, we simply going to creating here one plot line like that in the sections. If it is less than 1.5, you can say that this is one versicolor that you can see on here in a versicolor manner. This is how our machine learning actually classify in the form of data point. Okay, in the decision tree you can see on here. And then if the data is above this 1.5, we can say that this is a Virginica. This is a Virginica. Okay, that you can see on here. See how can actually classify this each of the portion, each of the data point in some kind of geometric plot that you can see. So that's mean this plot is nothing but about the Setusa. This one is nothing for the Virginica, and this one is nothing for the versicolor. Okay, so we have the three clusters that you can see on here. How can you actually classify them? Now, what is entropy in decision tree? Entropy is the measurement of disorder or impurity in the information process in machine learning. It determines how a decision tree chose to split the data. So that's mean in entropy we have two things. One is called checking for the disorder and the impurity, and also chose to split the data. That's called the entropy in decision tree. So let's take one examples by flipping one coin. So if I flip one coin, we have two outcome. One is called head, one is nothing but tail. That's when you have the 50-50 chances. One is purity and another one is called impurity. You can also checking this one. So let's taking one examples by understanding this entropy more well. So we have two dataset number 1 and dataset number 2. And you plotting this out in the form of a scatter. So we have the dot, black dot and the white dot, and also black dot and white dot intersections. And also you can see here we have a note called more knowledge is nothing but the less entropy. So if I see this data set, if I dividing this one portion, we can see that we have more amount of data. That's mean more amount of uncertainty. That's mean more amount of entropy. That's mean in this portion we having the nothing but the high entropy. But in here you can see here you can getting here the more knowledge on here. That's mean it having a less uncertainty. you can easily access, you can easily gain the knowledge from here. So it will have the less entropy. That's mean more knowledge you can gain, it's having a less entropy. Okay, let's try to checking the equation for the entropy so that we can also calculate it in the form of equations. So this is the formula for this entropy that you can see. Es is equal to nothing but minus p and log 2 base of pi, I mean p, this one, and also summation for that. Okay, I started from I equal to 0 and the c. So p is nothing but one frequentist probability of an element or the class. Element or class, that's mean this is nothing but aborting the target class. So let's say we have two class of yes and no. So how can you calculate the entropy for that, for these classes? So this is the formula for that you can, how can you return that? Minus p of yes log to base of p yes minus p no log to base of p no. This is our actual formula. This is our actual formula, and higher phi is nothing but our classes. If we have the three classes, we can also write in this formula like that: minus p yes log to base p yes minus p no log to base p no, or minus p other log to base p other. If we have the three classes having yes, no, or other, this is how you can actually create in the formula for the entropy. Now let's try to do some mathematics using this formula. So let's go to the next slide. So we have one examples. We have one table, which one having the feature called salary, age, and the marry. So if the salary is nothing but the 20,000, and if the age is 21, he cannot marry. He unable to marry just because of salary is low and age is also low. Okay, I just taking one examples. So if the salary is nothing but the 10,000, and if the age is 27, but he cannot also marry, unable to marry just because of his salary is nothing but less in the in this term, because salary should be the high, so you can marry. Okay, just one example, just यहाँ पर दे दिया भाई. So if the salary is nothing but the 45,000, is nothing but a real world scenario in the in the social right now. So if the age is nothing but the not social, actually society. So 28, should be the yes, he can marry. And if the salary is nothing but the 25,000 and if the age is 31, he can also marry, because बहुत उम्र हो चुका है, इसके बाद सैलरी भी ठीक ठाक है, चल जाएगा बस. So if the salary is nothing but the 12,000 and but age is nothing but 29, yeah, the age of the शादी करने की age बयस है, लेकिन शादी नहीं कर पाएगा just because of the salary. 12,000 to संसार नहीं चलेगा बस. So just taking one example, okay. So how can you calculate the entry for that? Just for checking the Mary one, I just taking this one as a target classes. So we having two things, yes and no. So if I see that we having the three no, let's taking the another color, green color. We have the three no. You can see on here we have the three no. So three no, and also two yes. You can see two yes. So how can you calculate the entry for that? So minus py, y is nothing but the yes, log to base of py minus pn log to base of pn. So we're simply going to calculate the pn by dividing with the total number of scenario or total number of classes in our data set in the form of row. We divide with the data or the no is actually available inside your data set. Again, total number of data divided by how many no it have or how many yes it have. So you have the two yes, so 2 by 5. So 2 by 5 on here. So how many no we have? We have the 3 no, and total data set we have the 5. Okay, so we got in here entropy as 0.97. So let's say if we have the one yes and rest of them is nothing but the no, so it should be like that, 1 by 5 and 1 by 5 and 4 by 5, because 4 is nothing but no in these examples. So 4 by 5 we having the 0.72. Let's say we having all of the values nothing but the no, or all of the values nothing but the yes. So we can get in here this one. So if all of the values nothing but the no, that's mean you don't have any yes. So yes should be 0 by 5, 0 by 5, and this is 5 by 5 log to base of 5 by 5. And if we calculate this one, we can directly got in here the value of 0. That's mean you can see here the minimum value for the entropy is nothing but the 0, and the maximum value is nothing but the 1. Okay, if we have the two classes. And you can also see that if the one class is missing, and all of the classes no or the yes, and you can got in the entropy as the 0, that you can see here. If we have the entropy of the class number 3, we have the 3 classes, the entropy should be greater than 1. So let's try to do some observations. So we have these observations, you can see here, more the uncertainty, more is entropy. For the two class problem, the mean entropy is 0 and the max is nothing but 1. So for the more two classes, in the mean entropy is 0, but max can be greater than 1. So both the log2 base is nothing but log2 and log e can be used for the calculate the entropy. Because you can see here, I am using here this log2 base. You can using here the log or log2, whatever you can use on here. Let's go on the next slide. So we having another examples. How can we calculate the entropy by plotting this default kernel density plot? So this our data set number 1 and our data set number 2. Let's try to do here yellow one, this one. So we simply going to plotting this one in the form of density plot, I mean KD plot. So we having this data set number 2 and data set number 1. So in the data set number 1, we can see here started from -1 to 1. This value ranges from here, and also you can see here the graph is quite low peaked. Okay, but this graph is look like the flatten. Okay, that you can see on here. That's mean in this peaked one we have the more knowledge in a short time. That's mean it have the less entropy, and if because this is a flatten for the data set number 2, it having the high entropy because it having the it take more amount of time for getting the knowledge from here. So this is how you can also calculate or you can measure the entropy from the density plot. So our next topic is about information gain. So information gain is a measure used to determine which feature should be used to split the data. See, if I go back, you can see here the entropy. Entropy it actually used to measurement of disorder and impurity also chose to split the data, but not feature. It will chose to split the data, not feature. But in the information gain, it will chose the feature as well. So it is calculated using entropy. Obviously, it is calculating entropy. If you see the equation, you can see here information gain equal to entropy of the parent minus weighted average into entropy of the children. I mean child. So simply information gain is a metric used to train decision tree. Especially this matrix measure the quality of the split based on feature. Root shooter feature should be used to split the data. Let's try to do some examples, taking some examples and try to calculating the entropy for the parent and try to calculating this information gain. So we having one most favorite data set that's called playing tennis. If you have the weather called outlook, temperature, humidity, based on that you can play tennis or not. So we have the 14 row. So how can you calculate the entropy for that? So we can simply going to divide them for the yes and no because we have the uh, 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 yes and no features. I mean our target classes. So we have how many yes we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's been 14. So 9 by 14 equals 9 by 14. So minus is missing on here. That's my bad. And then you have this minus 5 by 14. And if you calculate this one, you can getting the entropy called 0.94. So this is the entropy for the parent because this outlook is nothing but our root. I'm just taking this one. Now what I can do, if I see this one correctly again, which feature should be split in the data? See, which feature should be split into data? So I'm just going to taking at the outlook this one, and I am trying to dividing this one into three parts because in the outlook we have three classes. So this is called sunny, overcast, and the rain. And based on that, I am simply going to splitting the data into three parts based on the feature called outlook. So let's go to the next slide. So you're having a road node, that's our outlook, and we divide them into two portions, three portions: sunny, rain, and the overcast. So in the sunny portion, we have the 1, 2, 3, 4, 4, and 5 data. And for the overcast, we have the 1, 2, 3, 4 data. And for the rain, we have the 1, 2, 3, 4, 5. We have the 5 amount of data. We actually splitting them in the based on the features for the sunny, for the rain, for the overcast. Okay. So how can we calculate the actually entropy for that? So let's say we have three classes in our data set. So for sunny, you have the 5 row. For the overcast, you have the 4 row. For the rain, you have the 5 row. and you have 3 no and 2 yes and 4 yes, 2 no and the 3 yes. So for this case, we can simply going to say that entropy is nothing but the 0, because I don't have any no. That's mean if one class is missing, that's when entropy is going to the 0. So for this case, you can also calculate them, and you can got the entropy as nothing but the 0.97. And for this can you also getting here the entropy is called 0.97. Now how can we calculate this weighted entropy? So we can calculate it by dividing this number of features. So you have the 5 features in this case, so divide them 5 into 14, and we actually add it to our parent classes, because this is the parent classes. If I see the formula, you can see here, this is the e parent, and we already calculate the entropy for the parent. Now we need to calculate this weighted average and into e children. So we also calculate the entropy for the children, because we have the 3 child, Sunny, Rain, and then Podcast, and you can see here we have the entry for that. Now that's our weighted average. That is how we can actually calculate the weighted average. How many weight you have, and we can do the average for that. Simple. So you have the 14 row. We can divide it 5, divide it 4, and divide it 5. And after that, we can got in here our weight of the children. I mean, weight with children is nothing but 0.69. And after that, we can minus this one. We can got the information gain of the 0.25 for the case of outlook column. So you can also do it for the temperature. You can do it for the humidity. You can do it for the weight. So that's your homework to do that. That how can you calculate the information gain. Now let's go on the next slide and see our next topic about the Gini impurity. So this is also same like the entropy, because in the entropy you also calculate the impurity and as well as the disorder. Same thing using Gini, you can also, or Gini, you can actually calculate the impurity, same like the entropy. So in the entropy, we have the formula called E equal to minus P of ES log to base of PES minus P no log to base P no, if we have that two classes. So if you have the two classes, in the case of Gini, so the formula look like that. G is equal to 1 minus PES whole square plus P no whole square. This is how you can calculate the impurity using this Gini. So our explanation is completed. Now we're simply going to implement the decision tree from scratch using Python. We already know that decision tree is nothing but an tree structure classifier. That's been in decision tree we have a class called node. So first I'm going to importing here numpy first. Let's say numpy as entry. Then after that I'm going to creating here a class called node. So that's a class node. Then I'm going to passing here def. Let's say init. And then I'm going to passing here the self and the feature. Let's say feature equal to none. Then we have the threshold. Threshold is equal to none or none, whatever you can say, none. Then you have the left, we have the right, and we have the value. So for a node, we have those certain types of parameter. One is called the feature, that how the node is look like. Then we have the threshold value. Based on certain threshold, you'll divide them, split them into left and right portion. Then you have the left variables, I mean left node portion, right node portions, and the value, I mean value of the node. Now I am simply going to initialize all of the value here. So what I can do, you can using here self dot feature is nothing but equal to feature, and then you have the self dot threshold is nothing but the threshold. Then you have the self dot left for the left child, so it should be left. By default, I am simply going to pass it here the none, but when you're creating here the decision tree, you need to passing here the features, threshold, left, and the right block as well as the value. So you have the self dot right is equal to right. Then you have the self dot value is equal to value. So you're creating here the node. So if I see the node, you can see the how it node look like. And if I see this one, you can see here this is nothing but one main class of the node. So you can also passing here the value. Let's say I'm going to passing here features. Let's equal to 10. And if you wanted to see this one node, and let's say node, and then you can access the feature column from here. Let's say node dot feature. Okay, then you can see 10. because we passing here the node as a 10. That's when our class is working very fine. You can also access here the value. Let's say value. You can see here value is right now because it's not passing yet. Okay. So now what I can do, I am simply going to creating here a class called decision tree. So let's create a class decision tree, and inside that we simply going to creating here same thing. Let's say def init, and then inside that I'm going to passing here the self and one max depth. Because if I see in the slide decision tree, you can see here decision tree is nothing but one tree structure, just like the tree in the DSA. So in here you can see here this is nothing but one tree, it having one root node, then having some left child and the right child as well. That's mean it also having a depth of the tree. Okay, so it's simply going to pass in here the max depth. So by default I'm going to pass in here the nan, and then I need to actually initialize all of the things. So we have the self of max depth. Let's say max depth is equal to none. Okay, no, max depth equal to max depth, because you're going to taking it from the parameters. Okay, I mean from here. And after that, what you need to do, you need to also initialize here on root of the your tree. So let's say root. I just assume that you have the knowledge about the DSA, I mean tree and graph, so you can understand it easily, because some kind of technique called the recursive technique that I'm going to using it here for calculating the left child and the right child on here. So let's say none, and then after that I'm simply going to creating here a function called feed, because each of the machine learning algorithm it have a function that's called feed and the predict. So the feed is nothing but used for training the model. So in decision tree, we using here a functions called growty, and using growty we can actually do the predictions. So we can pass in here the self of the x comma y, and then we're going to using here self dot root is equal to self dot grow tree. Using grow tree, this method, I am simply going to, I mean we simply going to actually do the predictions. I mean we're going to training our decision tree. So we're also creating here these functions called growty, but we are not creating yet. We have to create it later on. But first, I am simply going to actually creating here functions that's called a Gini impurity. So if I go the slide again, then you can see here we having one property called the Gini entropy. I mean Gini impurity. Sorry, it's also same like as the entropy that we already discussed on that. So you can also using here the entropy, or you can using here the Gini impurity. Okay. So I am simply going to creating here a functions called Gini impurity and try to implementing this method. So I'm going to go on here, and then I'm going to say that we have a functions called def Gini impurity, which is nothing but taking the self and the y itself. Okay, y is nothing but our target column, because if I see the structure, I mean see uh, the formula of this Gini impurity, you can see here 1 minus p of yes and the p of no. So here p is nothing but one elemental class, probabilistic class. That means it's nothing but our target class. So our target class in this case, it's nothing but the y. So we can pass here the y. So what we have the count of the yes and the no. So you can also do the counting using this np.unique. Let's say np.unique, and you're already importing here this numpy. Okay, so np.unique, you're going to passing here the y, and you can passing here the return counts. Let's say return underscore counts is equal to true. So this will return me two things. One is nothing but same thing, and we have the count. It's not the index number and the count of the yes and the no for the each of the target class. Let's say I have one table, this table, this table. I have in this table. So if I pass in this inside this Gini impurity function, it will counting all of the value, how many value it have, how many value it have, and also it will actually counting here number of unique count for the yes and the no, how many yes we have and how many no we have. And we see that we have the yes is called nothing but called 9, and no is nothing but the call 5. It will counting this one, and after that what it will do, it will simply going to using this formula p yes yes whole square plus p no whole square. Okay, like that. So then after that what I can do is simply going to calculate the probability of that. So how can we calculate the probabilities? So we can calculate the probabilities by using this formula. Let's say probability probabilities, okay, probabilities is equal to count, I mean this count, how many count we have, that we can divide them with the length of the y. Why? See, PES, it's nothing but counted. How? If I go to the entropy, you can see here it is counted total count, total count, total count divided by n. This is nothing but how we can calculate the PES, right? So you have the total number of count, and then we are going to simply go in total number of count is nothing but the full dataset count, and you have the count of the each uh, unique ES or no. Okay, so we can simply going to divide them with the length of y, because length of y is nothing but giving here the total count of our table of the data sets. Then in the counts, we're simply going to give it here the unique count for the each of the categories. Okay, so now we have the probabilities. We can simply go to using the formula right now. Let's say return here 1 minus np dot sum. Okay, because you see this Gini impurity function, you can see here this is the Gini impurity actually, and we need to also do the summation of that. You can see plus summation and also 1 minus, so 1 minus and n period sum, and you have the probability, I mean the probabilities of the uh, each of the actually features for the yes and the no, because if the y, it will pass in here two values, yes and the no, and it will store it differently inside this count. Okay, so we can simply go to using here this score, because it will try to summing this out and also calculate the score for the each of the uh, uh, unique columns. Okay, I mean unique value. Now this is called the Gini imperative, and after that we having another term that's called the information gain, that you can see here. Information gain is a measure used to determine which feature should be splitted. Now using information gain, we are going to selecting here the features. So in here we actually taking the examples about the outlook. So if the value of the outlook is greater than the temperatures, so you can also consider this temperature as a information gain or the splitting of the factor or the best splitter. So what I can do now is simply go into actually creating a function called information gain, and where I need to calculate here the entropy of the parent, okay, or the Gini of the parent, because Gini impurity and the entropy are the mostly same. Then you have the weighted average, and you also entropy of the children. So let's go on here and try to creating here a function called information gain. Let's say information gain. So inside that, you can pass in here self, and you to passing in the parent, then you to passing in the left child and the right child. Okay, right child. So why left child, right child? Because see, in the information gain, we have a certain number of features, because from those feature, we're simply going to calculate the information gain for the each of the feature column. So it will convert it into just like the left child and the right child, because it's nothing but n node. Now inside that, we're simply going to calculate the weighted of the left side and the right side. So see, why left, right? Just go on the horn here, and I'm simply going to draw one thing just in this section uh, in here. Okay, so see, it's nothing but a root node, and we have the left child, we have the right child, and then again we have the left child, we have the right child, we have the left child, we have the right child. Because decision trees look like the tree, that's we need to go on this left child, we need to go on this right child as well in the same time, and recursively it will go until they actually found the leaf node. Okay, so that's mean if we calculate the weight of the left, I mean to calculate the weight of the left and the right side, and after that we can do the summation of that. So let's go on here again, and then let's weight left. So how can you calculate the weight of the left? We need to calculate the left child length, left child length, and divided by length of the parent, length of the parent. See how it's still coming. If I go on here and see this one, this formula, you can see here. Let's try to take in the highlight. You can see 5 by 14. 14 is nothing but the total length of the parent. Okay, this parent means it's nothing but the parent is this parent, entry with the parent, full data set, it's called the parent data set, right? So full parent, the entropy, and after that we need to divide them with the each classes, because we divide them into three classes based on the outlook: sunny, overcast, and the rain. That's mean when you calculate the weighted entropy or weighted of the left side or the right side of the node, we're going to using here this 14 divided by 5, and where 14 is nothing but the length of the full data set, and 5 is nothing but of the each portion of the features column. Okay, features, and because we divide them into two features, right? So we go on here, and this is how we can calculate the weight left, and we have to calculate the weight right as well, because this is nothing but this is nothing but one tree itself. So that's the length of right child divided by length of parent. Now we have the weight average. Now what we need to do now, we need to uh, calculate the Gini impurity, I mean entropy, because we are using the Gini impurity. In this case you can also using the entropy, because it's up to you that how can you actually use the Gini impurity, and the entropy is similar. So now we can simply go to returning here, let's say returning here self dot Gini impurity, and inside that you can pass in here the parents itself, and then this our formula, see parent, and then you're going to using here minus, see the formula again, the information gain kidhar gaya bhai, e parent is nothing but the, let's say, entropy of the parent minus weighted average. Okay, weighted average of the right child and the left child. So again, and we have the weighted average, let's say weight dot left. Okay, weight left, sorry, weight underscore left, sorry, weight underscore left, this one underscore left, into we have the self dot Gini impurity, and you're going to pass in here the left child. Okay, let's say left child, this left child is coming on here. Okay, this left child, because you need to also calculate the child entropy of the child as well, so you need to pass it here, and you need to actually multiply them. If I go it again, and you can see multiply with them with each child, number of child, because it have the two child, left child and the right child of the tree. That's why you're using here this one. Now after that, what I need to do, I need to simply go into using here the plus, because we have the two child as well. So one is the left child, another is the right child. So let's say weight into, let's say, right into the self dot Gini impurity, and then I'm going to passing here the right child. Okay, right child, that's it. Okay, this is how the actually information gain actually work. Okay, we already implementing here two things, information gain and the Gini impurity. Now we have the entropy, I mean this is called entropy, and we also have the information gain. Now if I go on here, you can see here, based on this information gain, the data of each internal load of the decision tree, okay, it actually split it. Now we need to checking that which one is the best split, which one is the best split, because we have the feature right now, and which one is the best split based on this information again. So let's go on here and try to creating here a functions called best split. So let's say def, let's say best underscore split, and you're going to passing here self comma x comma y, and then we are simply going to creating here a variable called best gain equal to, let's say, -1. It will storing here the best gain is equal for that. And after that, we simply going to add here two things. One is the best feature, I mean which one is the best features, and as well as the best threshold, because if I see that in our node into passing here one variable called threshold, this is threshold is nothing but the threshold value for our features. Okay, so let's initialize it 9 itself. So we have the two variable best gain, where we're going to storing here our best gain score, and the best feature and the best threshold we're also creating here two variable for that. Now we're simply going to getting here all of the features. Let's say for in range, and we can getting here the feature from the actor shape. Okay, actor shape, in the actor shape we have the all of the features. Okay, so let's say features. So why this x dot shape of one? Because see, the shape is look like that. We have the row and the columns. So here you can see row is nothing but all of the row, and column is nothing but of the column name. That means column is nothing but our features name. So if it's nothing but index number one, if you see that it's like look like that. For the row it is index number one, and for the column it is index number. Sorry, for row it is index number 0, and for the column it is index number 1. So that's why I'm using here this x dot shape is equal to 1. Okay, so now we have all of the features of the x, because in decision tree you can pass in here multiple number feature results in the x features, and we're going to taking all of the feature from here, the column name, Now we can simply going to calculate the unique value for that. Let's say np dot unique, and you're going to passing here x, and you need the all the row and the features, all of the features. So it's the feature because it coming in single feature. Let's make it at a singular number, and then I am simply going to store it as a call thresholds. So this is nothing but our threshold that we got on here. I mean my unique value for that. So after that, we simply going to getting all of the unique value from here, because it can be the multiple, because it having the multiple number of row in the column. Now from here, we're simply going to splitting them. If I go on here again, then you can see that in the data set, we're splitting them into three parts: sunny, rain, and the overcast. This is called the splitting part. This is called the splitting part. So that's mean you need to do the splitting on here in the sections. So this is how we can do the splitting, right? Because we have the all other features, just like outlook, then we have the temperature, we have the humidity, because each of the column, I need to taking each of the columns and we need to do the splitting of that. So if you're splitting this outlook column, we have the sunny, we have the overcast, and we have the rain. If I splitting this temperature, we have the hot, we have the mild, we have the cold. Okay. If you're splitting this humidity, you have the high, you have the normal, and we don't have anything else. Okay. Then if I split this wind, you have the weak and we have the strong. Okay. This is how it actually creating is splitting, and it will creating here this kind of chart inside our decision tree. And then you can calculate the information again, and we are going to selecting the best of that. So this is called the best splitting, right? Now you have the threshold, all of the threshold, because each of the column it having different threshold of the each of the units based on the features. Now you can simply go to using here the threshold. Let's say for threshold, threshold, threshold in threshold. Let's say thresholds. So you have the up threshold value. Now you can simply going to calculate the marks for that, for the left marks and the right marks, because it's nothing but in tree itself. So how can you calculate the left marks? Let's say left marks is equal to x, and we have the all of the row. Okay, all of the row, I mean all of the features. Then we have the all of the features. Then we simply go into features. It should be the number, and then we simply go to using here the threshold. So this threshold is nothing but our information gaining threshold, like that. So it will first checking that if the threshold value is nothing but the less than the features column, it will go to the left marks. If I go on again slide, you can see here I getting here on tree. If it is nothing but the less than, if it is less than here of this root node, it will directly go to this left marks. If it is greater, it will directly go to the right marks, okay, or the right child. So this is how the tree actually work. So creating here on this, if it is all of the value is nothing but less than threshold, it will directly go to the left marks, and otherwise rest of them value is going at the left marks. So you can using here this one, that's left marks. Okay, opposite of the left marks, this is called the right marks. Now we can calculate the information gain for that you created. That's the information gain. This is self dot information gain, and inside that you can passing here this y, and you're going to passing here the y dot left marks and the right marks. That's it, y of the right marks, I mean right marks of the node. Then this is nothing but our information gain. Now you can check that what is the best split. So you can using here and thing, let's say gain, it's nothing but the best gain. If it is a greater than best gain, then you simply going to replace this best gain into the gain. And after that, if you have the best feature, this best feature, then you can make it as the best features. And then if we have the threshold, this will replace the best threshold. This is called the threshold. Okay, see threshold. So you have the thresholds. Threshold is coming on here, checking to the threshold, each of the threshold, and you're going to give it here. Now we can returning here. Returning here the best feature and the best threshold. So now we're splitting the data, the best splitting, and also implement here the information again. We also getting here the best split. Now we are simply going to creating here our this grow tree. Okay, we're going to grow tree. So until they'll go to the leaf node. So we can simply going to creating here this one. This is called the training of that, because feet is nothing but called the training. So let's say def. I'm going to using here the grow tree, and here you can passing here self, x, and y, and depth. Let's give it a depth equal to 0. By default, I'm going to passing a depth to the 0 because it is starting from the root node. Now we have the x dot shape. So from x dot shape, what I can got, we can got the number of samples and the number of features. That's the number of features. How many sample it have is nothing but the number of row and number of columns. And column is called the features in the data set. Now we need to calculate the number of classes itself. How many classes it has, because it can be the multi-class classification as well in the target class. So it also calculate the length of the np dot unique, and you're going to passing here the y. So you have the number of classes. Now we're simply going to creating here on a stopping criteria. So just because of, we're simply going to creating here one recursive call here, because if I see on here, this is nothing but a recursive call. You can say recursive call. So let's try to implement this one first. So what I can do, we need to calculate the left marks first. Let's say left marks. So we can calculate the left marks like this way. Let's say from all of the features, then you can using here the features. Okay, all of the features. So then we're simply going to using here the threshold. Okay, this threshold is coming on here. It's nothing but a start on here. Okay, so you have the threshold value. So here you can get the threshold value, it also start it. So you can start it from the best split. Let's say self dot best split, and inside it you can pass in here x and y. So you can got in here two things. One is the feature and the threshold. Because in the best split we have the all of the best features and the best thresholding value from the best split. Now you have the best split, the feature and the threshold. Now we're checking for the left marks and the right marks. Let's say right marks. So right marks is nothing but the opposite of the left marks. Let's say left marks. Now you have the threshold value, you have the left marks. Now we can simply go into call our recursive call. Okay, so let's do the recursive call. Let's say left is equal to self dot grow t, because I am just going to calling here a recursive call on here from on this same functions, the left side and the right side. So let's say grow t, we're going to passing here the x, and we're to passing here the left marks, and we're to passing here the right marks. So let's say sorry left marks, sorry, and then we're to using here depth plus 1. So that's why depth is nothing but initialized as a 0. It will starting increasing the depth of that of the each of the node for the left side and the right side. So to calling this out again for the right side as well. Let's say right side self dot grow, and we to have the right marks, and we have the right marks. Now in recursion you have one base case. Okay, so it's also called the stopping criteria. So we have one base case. So it also initialize this base case here. So how you actually do the depth of the node, so depth of the tree. So if the max depth is nothing but the max depth that you passing here is equal to this depth that is passing, so you can stop, because this is nothing but our stop cases. If I go to the max depth, this max depth, so we need to stop them, because we got here our leaf node. So what you can say, let's say if it's better, we can take in some spaces. If the depth is equal to max depth, because it will increasing the depth. You can see depth starting from 0 to increasing recursively. If the depth is equal to max depth, okay, I mean self dot max depth, because we already initialized this one. Max depth, yes, max depth. So it's equal to max depth, or the number of samples, I mean this samples, number of samples is less than equal to 2. That's means just having one features. If just having one features, okay, just one feature, just this root node, so we need to stop it. Or the number of classes is equal to 1. If we have the number of classes not even 1, that's mean our entropy is 0. This Gini impurity is 0, because you already see that for this one cases our entropy is 0. You can see on here, our entropy is 0. Just mean you don't need to actually calculate anything else. So we can simply go into returning here our node. Okay, returning here our node. So let's try to return here. Let's return here at the node, and you're going to passing here the value because we don't have anything else. So you can passing here argmax. So we can passing here the value. So if I go on here, so we're simply going to taking all of the argmax of the all of the node of the leaf node, and you're going to creating here the bin count of each of the data point. So let's try to pass it here. Let's say np.argmax, and you can using his np.bin count, and then you're going to returning here this one. Okay, that's it. Now if this process actually happening, the process actually happening, and we simply go to returning here one node. That's a node at last. So we're going to passing here the features. So feature is nothing but our feature. Then we have the threshold. Threshold is equal to threshold, and then you're going to passing here the left equal to left, and the right is equal to right. So we're creating here this grow tree functions. I mean, this is nothing but our training. Now after that, what I can do is simply going to do the predictions. So how can I do the predictions? Let's try to using here def predict, and we're going to passing here self and the x, and then you're going to using here a return statement. Let's say return np.array, and inside that you need to creating here a function itself, which one is nothing but the traverse of the root node. If I go on here to do the traversal of that, traversal is nothing but checking for that. If you do the traversal, you have the two traversal technique in the tree. We have the DFS and the BFS. Okay, BFS is nothing but go to the level wise, and DFS is go to the depth wise. Okay, so what I can do is simply going to go on here, and then I'm simply going to, I'm not going to initialize here or creating here the BFS DFS, because or do need to actually creating here the BFS DFS itself. We can simply going to using here level wise or the depth wise actually or level wise. Okay, we can using here the level wise actually what is called traversal tactic. So you can call it here, let's say self dot traverse tree, and then inside that you can pass in here x comma self dot root, because you're starting with the root, and here x is nothing but for xi in capital X, nothing but the features of that. Now to defining here the traverse tree. See, DS is important here. If I don't know about the DSA, so how can I building this one? मुझे तो कुछ समझ नहीं आता ना भाई, यहाँ पर रिकर्सिविटी कैसे कॉल हो रहा है, हाँ, इसलिए DSA आना चाहिए. If you know about the DSA, you are being a gem in the field of machine learning. Okay, so DSA आना चाहिए, नहीं तो भाई मैं इसको इंजीनियर नहीं मानता हूँ. इंजीनियरिंग का मतलब एक्चुअली क्या ना, बहुत सारे फील्ड है ना, तो इसमें जो कंप्यूटर साइंस में है ना, उसको मैं नहीं मानता हूँ. डीएसए आना चाहिए, बस डीएसए आना चाहिए. तो वी आर क्रिएटिंग हियर दिस ट्रावर्स फंक्शंस. तो इसके बाद क्या करेंगे, तो इसके बाद मैं फर्स्ट चेक करूंगा इफ नोट इज एम्प्टी तो नहीं है भाई. इफ नोट डॉट वैल्यू इज नॉट नन, इज नॉट नन, none, it's mean it having the value, we can returning here the node. And then we're going to checking here if x of node dot feature is less equal to node dot threshold, then we can say that we can simply go to returning here self dot traverse t. Okay, traverse. So we already using here and recursive call here because we're traversing the tree. This is nothing but the base case. Okay, so we're simply going to keep going. Recursive is nothing but a magic function. It's just like a magics. Okay, if you actually creating here just one node for that, one base case for that, it will automatically calling this function again. Okay, so we're actually creating the base case, and we're going to check in that if the node feature is less than of the threshold, then you can go to the left child, and then you're going to go to the right child. If it's greater than that, you can directly go to the left child, and until it will actually go to the value of that, I mean the leaf node. So we can simply go to passing here x into node the left, and then we're going to using here if of, okay, because I am not going to actually discuss here the DSA here, because DSA is the basic things. So you need to run about that. Let's say return here, okay, should be return, okay, return here the self dot traverse tree, and you can pass in here the x and the node dot right. Okay, so that's it. So now we can run in this out, and we see that any error or not. Okay, we don't get any error. Okay, before actually creating the decision tree, you need to have knowledge about the recursions and the binary tree as well. That how it will create it. You can see here actually using here two functions. That's called grow tree and the traverse tree. Okay, this is nothing but one recursive call, because recursive call होता जा रहा है होता जा रहा है, तो recursive में just एक केस दे दो, बाकी सब वो केस वो सॉल्व कर देगा बस. Okay, TP इसके बाद लिंक लिस्ट सब कुछ में आपको recursive भी यूज करना पड़ता है बस. So now let's take in some example uses. So let's take in here x is equal to, let's say, np.array, and then I'm going to using here, let's say 1 comma 2, say 3 comma 4, and that's using here 5 comma 6, and then that's using here 7 comma 8. This is nothing but one example data set. Let's say np.array, and then inside that I'm going to pass in here, let's say 0 comma 0 comma 1 comma 1, like that. Okay, then I'm going to using here this tree as a decision tree, and then I'm going to pass in here the max depth. Okay, let's say max depth is equal to 3. So it will creating the depth of the tree is nothing but the 3, and after that it will not going that. So you're going to using here 3 dot fit, and you're going to pass into the x and y, and then you have the prediction. Let's say prediction is equal to 3 dot predict, and you can pass in the x. Okay, so these are our predictions, and let's see we got any error or not. So you're having so many error. Let's say counts. Okay, it may be happening just because of a human error. Okay, it should be counts. Let's see any error or not. Okay, it's gone, it's running. Cool. Now let's see the predictions. So that's our predictions. We got in here the prediction as well. Now let's try to using it one data set called iris, because we already discussed about the iris data sets. Okay, so you have the three types of things: Fetusa, Virginica, and Versicolor. Okay, so I'm going to import it from the Scikit-Learn. Let's say from a Scikit-Learn dot dataset, because it's available inside the dataset. That's why I'm actually importing the Scikit-Learn. That's iris, and then from Scikit-Learn dot model selections, I'm going to importing here the train test split. Let's say train test and split. Okay, cool. Now we need to loading here this iris dataset. Let's say load iris, and it will give me two things, not one things. That's iris, and it having the two things. One is data and another is target. Let's iris dot data and iris dot target. Okay, so we have the x and y. Let's say x comma y, and then we need to split the data, right? So let's say x train, x test, y train, the y test. So in the next couple of video, I'm simply going to actually cover up that how can you creating the train test and split without using this Scikit-Learn module, so that you can also create it from scratch. Let's say x comma y and the test size. Don't worry about this code. I'll try to make you pro in this machine learning field. Let's say random state is equal to, let's say, 42. Then I'm simply going to creating here this decision tree, and then I'm going to passing here the x train and the y train. So it should be the x train and the y train. Let's say y train, and it should be our x test. So it's our x test, and you have the predictions. So this is how the prediction look like. Okay, You can also calculate the accuracy for that. So how can you calculate the accuracy? You can calculate the accuracy using, let's say, np.mean. You can get the mean value of the prediction. That is, the predictions is equal to the actual value. Let's say actual value. So you're getting the accuracy on here. So let's say accuracy. So accuracy. So accuracy is 1. We know that in the decision tree, our model is go in the problem of the overfitting problem, because it is working very well in the trained cases, and test cases is not working well in some other cases. But you see that accuracy is 1 because it is a simple data set. Okay. So this is how we can actually implementing here this decision tree without using an SQL module. So I hope you like this series. I hope you enjoy this tutorial. So make sure to subscribe our channel. Just hit the bell icon so that you can notify how a new videos coming from the Knowledge Doctor. Okay. So thank you and bye bye. Namaste.